Hello friends, welcome to our new lecture of signals and systems. Today we are going to learn about time scaling of continuous time signals. Now, what is scaling? Scaling means changing the speed or the duration of the signal in time domain. So, now I will be playing you two clips, clip 1 and clip 2. New lecture of signals and systems. New lecture of signals and systems. Now we have found out that clip 1 is the same words but in an accelerated fashion. Both clip 1 and clip 2 are saying the same thing, are passing the same information, but clip 1 is the accelerated form and clip 2 is little slow motion, right? So this is nothing but time scaling, which we are going to study today. Let's see. Suppose xt is a continuous time signal. Then the time scale version of xt will be represented by yt equal to x of alpha t, where alpha is the scaling factor, where alpha is known as the scaling factor. Now alpha can be the scaling factor alpha can be greater than 1 or the scaling factor alpha can be less than 1. Now, if alpha is greater than 1, then our signal will be a compressed version. That is, our signal will undergo compression. That is similar to clip 1. And if alpha is less than 1, then our signal will undergo expansion in time domain that is similar to clip 2. So I hope you can relate now. There are two type of time scaling. One can be compression and one can be expansion. Let's take an example. Suppose xt is a signal. Xt is given as a square signal -2 to 2 1. Mathematically we can write xt is defined as when t is less than -2, xt is 0, the value of xt is 0. When t is between -t is less than equal to t is less than equal to 2, xt is 1. And when t is greater than 2, our xt is 0 again. So this is our signal xt. Now suppose in case 1 we are undergoing yt equal to x of 2t. We can see here 2 is greater than 1. So as stated above, our signal xt should undergo compression. So let's say mathematically. So we can see here what will be the changes now. See, now as because of the scaling, our t is replaced by 2t. So we will replace here all the definition of x and the time domain will replace all the t's by 2t. So let's do that. So t will be now 2t, then minus 2 is less than equal to t will be now this will be now 2t, this will be now 2t, then minus 2 is less than equal to t is less than equal to t 2 is b minus 2 is less than equal to 2t is less than equal to 2, and this definition will be 2t is greater than 2. So now taking the 2 in the right side of the inequality, t will be finally less than 2 by 2. If we will take this 2 to the right side, then it will be minus 2 by 2, that will be minus 1. Then if we will take the 2 in the left side, then it will be minus 1 less than equal to t will be less than equal to 1, and here it will be in this line it will be t will be greater than equal to 1. So here we can see that our definition of signal this will be yt. Our definition of the signal yt has been changed in time domain because of the scaling factor 2. Because of the scaling factor 2 that is greater than 1, our definition of yt has been changed accordingly. Now if we plot the yt accordingly, then we can see that from t is less than minus 1, yt is equal to 0. T is less than, let it be this line, this is minus 1, and this line, this is 1. Then t is less than minus 1, yt is 0. T between minus 1 less than equal to t less than equal to 1, yt value is 1. So yt value will be 1 in this section, and from t greater than 1, yt is 0. So it will be 0 again. So this is our value of the signal yt. So we can see that this is our case number 1. When we have taken yt equal to x of 2t, then as stated above, we can see that our signal is compressed. We can see clearly that our signal is compressed. Now let's take case number 2. Case number 2 when yt equal to x of t by 2. Yt is equal to x of t by 2. So we can see now this time our scaling factor is 1 by 2. This is less than 1. Our scaling factor is 1 by 2. This is less than 1. So as stated above, our signal should undergo this time expansion. So our signal should undergo expansion this time. So let's see it by the definition wise. So let's plot. So yt equal to this time. So okay, to make it more clear, I will write the definition of xt again and make the changes there. So our xt was 0 when t less than minus 2, and between minus 2 less than equal to t less than equal to 2, our xt was 1, and t greater than 2, our xt was 0, right? So now we are trying to write yt. Now we are trying to develop yt from xt, right? Now we are trying to develop yt from xt. So here we can see, now this time our yt is equal to x of t by 2, right? So what we'll do, we'll replace t by t by 2, right? We replace t by t by 2. So this t will replace by t by 2, right? And similarly this t will replace by t by 2, and again this t will replace by t by 2. So just do the calculation. So if we'll take the 2 to the right side, then our definition will be, this definition will be xt by 2, this is the definition of yt, will be t less than minus 4, right? And this one will become minus 4 less than equal to t less than equal to 4, and this definition will become t greater than 4. Now let's plot this. Now let's plot this. Now let's plot this. We can see that if we extend this, and now we are plotting our case 2 right now. So from t less than minus 4, our function yt is, this is the definition of yt now in case 2, when t less than minus 4, value of yt is 0. So this is the axis 2, this is, let it be 3, let it be minus 4, and let it be minus 3, let it be minus 2, okay, let it be minus 1, let it be 1, let it be 2, let it be 3, and let this be 4. So when t is less than minus 4, our value of yt is equal to 0. When t is between minus 4 to 4, our value of yt is 1. So from minus 4 to 4, our value of yt is 1. And when t is greater than 4, our value of yt is 0. So when greater than 4, our value of yt is 0. So I hope now you can see the clear description and can relate with the two sound clips that I played earlier, that when the original signal was defined from minus 2, the original signal was defined in time domain between minus 2 to 2. The time compressed version of the signal, when the scaling factor is 2, is compressed, and now the time axis become from minus 1 to 1. And in case 2, when the scaling factor is 1 by 2, that is less than 1, then our signal expanded in the time axis, and it is visible here. Now we will learn one shortcut to solve quickly this kind of time scaling problems. So let us take the same function xt. Let us take the same function xt. So as we know, between minus 2 to 2, xt was defined like this. Xt's value is 1 between minus 2 to 2. This is the time domain. So suppose in case 1, suppose we are undergoing yt equal to x of 2t, where the scaling factor 2 is greater than 1, then what we will do? See, always remember, when the scaling factor is greater than 1, then we will divide that scaling factor directly from the time axis. So what we'll do? We will divide the scaling factor. This is 2, right? So we'll divide directly from the main signal like this. Okay. So after dividing, what we'll get? This is minus 2 by 2 will get equal to minus 1. 2 by 2 will get equal to 1. So now the new signal will be like this, from minus 1 to 1, and this is our new signal. So this is case 1. It's a shortcut method. We can perform this in competitive exams. And suppose in case 2, suppose yt is equal to x of t by 2, yt equal to x of t by 2, then the scaling factor is 1 by 2. This is less than 1. So in this case, what we have to do? Let's erase the earlier example. It's defined between minus 2 to 2. So what we'll do? We just multiply the denominator. With the original signal time axis. That is, multiply it by 2 and multiply it by 2. Just multiply the denominator. So what we'll get? This one will get equal to minus 4. This one will get equal to 4. So this will be our new signal yt. So let's draw it nicely below. So our signal will somehow, it will be stretched from here to here. It will be minus 4 to 4 in the time domain. So we can see this is the shortcut method for time scaling of continuous signal. Thank you.